All right, this is the 2021 FRQ for Taylor's polynomials. They give us that a function g has derivatives of all orders for all real numbers. The Maclaurin series for g is given by this g of x. A, state the conditions that are necessary to use the integral test and determine the convergence of 1 over e to the n. Use the integral test to show that 1 over e to the n converges. Now, if AP didn't ask me to do this by the integral test, we would not do it by the integral test. This is definitely something I would do a geometric from. Okay, but they asked us to do the integral test. Part B. Use the limit comparison test with this series, 1 over e to the n, to show that the series g of 1 converges absolutely. Okay, so first thing we need to recognize is that it wants us to do convergent absolutely, which means we're going to get rid of this alternating part. Part C, determine the radius of convergence for G. Now this gets kind of weird, but this right here we've been working with was G of 1. Now they're saying go back to G. This is G over here. So we want to find the radius of convergence. D, use the first two terms of the series for G of 1 are used to approximate G of 1. Use the alternating series error bound to determine the upper bound on the error of the approximation. So our approximation is the first two terms, which means our third term is going to be our error. Now our first term here would be n equals 0. Our second term would be n equals 1. So our third term would be n equals 2. This is the term we want to use for the error. The first thing they asked us to do was to state the conditions for the integral test. To use the integral test, the series must be positive, continuous, and decreasing. So we want to use the integral test to show that this series converges. Okay, so the first thing we have to do is write it as an improper integral. Notice the series starts at 0, so we're going to start our integral at 0. Then we're going to integrate e to the negative x. The first thing we do is rewrite it with a limit. So limit as b goes to infinity. After we write it as limit, we need to integrate it. E to the negative x, its integral is negative e to the negative x. Then we're still going to plug in the endpoints just like you would. So negative e to the negative b plus e to the 0. And you really want to think of this as negative 1 over e to the b. As b goes to infinity, this is going to infinity, so this whole ratio is going to 0. So this is going to 0, which means this is going to 1. Now, since this is finite, we know that it converges. The integral is finite, which implies it converges. So, by the integral test, the series also converges. Make sure you write that sentence. So B. G of 1 is equal to negative 1 to the n over 2e to the n plus 3. So the absolute value of g of 1 is just 1 over 2en plus 3. So we're asked to do the limit comparison test. So the limit comparison test says we're going to take any two series that we want to compare, and they told us we wanted to compare this g of 1, which was 1 over 2e to the n plus 3, and we're comparing it to 1 over e to the n. So we're comparing it to a series that we already know what it does. If this limit is finite and non-zero, that means they both converge or diverge together. Whatever the known series does, the other one does. So then we're going to multiply by the reciprocal. And you think about as you go to infinity, this plus 3 means nothing. So our limit is going to 1/2. Since this is finite and non-zero, the series compare, which means one of them, if one of them converges, the other one converges. If one of them diverges, the other one diverges. Since 1 over e to the n converges, so does g of 1 in absolute. Make sure that you show that you're really taking the absolute of that so that you're not considering the alternating part. The only time we get a conditional convergence would be with alternating series test. Now the radius of convergence, we always use the ratio test unless it's geometric. So I want to know the radius of convergence for g of x. And that was the summation, negative 1 to the n, x to the n, 2e to the n plus 3. So we're going to look at the limit as n goes to infinity, an plus 1 over an. So the first one would be negative 1 n plus 1 x to the n plus 1 all over 2e to the n plus 1 plus 3. And I'm immediately going to multiply by the reciprocal. Now we go through and cancel whatever we can. This negative 1 to the n is in absolute values, so doesn't mean anything. I have an xn on the bottom, and I've got an xn plus 1 on the top, so I have one extra x up here. Now looking right here, I really cannot cancel out those e to the n's. But if you're thinking about infinity, these 3's really don't mean anything. These 2's are on the top and bottom. So it's really e to the n over e to the n plus 1, so it's really going to be 1 over e. So this limit is the absolute value of x over e. And remember, for the ratio test to converge, you need this less than 1, which tells us that our radius of convergence is going to be e. So D. For a convergent alternating series, the error is less than the first omitted term. So our error is going to be less than that third term in absolute value. Remember, our function was g of 1, and it is negative 1 to the n, 2e to the n plus 3. So we're plugging in, we decided it's going to plug in n equals 2. So that would be positive 1 over